Let's explore circular linked lists. We will delve into their implementation and the various operations that can be performed on them. A visual representation is provided on the screen, showing a circular linked list with a head pointer and nodes containing the values 10, 20, and 30. The last node points back to the first, creating a closed loop. So, what exactly is a circular linked list? Well, it's a special kind of linked list where the last node doesn't point to null, but instead it points back to the very first node in the list. This creates a circle, hence the name circular linked list. Because of this circular nature, there's no concept of an end in a circular linked list. You can start at any node and traverse the entire list. The main features are that the last node points back to the first node, there is no null at the end, any node can serve as a starting point, and traversal can be done in a circular manner. Circular linked lists come with some advantages. Traversal is simplified because there is no need to check for a null value. Insertion at the beginning and the end can be performed in constant time. These lists are suitable for applications like implementing round-robin scheduling algorithms and for efficient queue operations. Memory allocation and usage are also more efficient. For example, in round-robin scheduling, processes are arranged in a circular fashion, and the CPU is allocated to each process in turn. Here's how a node in a circular linked list is typically structured using Python code. Each node has two main parts: the data field, which stores the value, and the next pointer, which points to the next node in the sequence. The circular linked list class contains a head pointer, which points to the first node in the list. In a circular linked list, the next pointer of the last node points back to the first node, creating a loop. Let's look at the code to create a circular linked list. First, check if there are any elements to create. If the list is empty, then simply return none. The first node is created. The remaining elements are added to the circular linked list. The new node is linked to the current node. The current node is updated. Now it has to be made circular by connecting the last node to the head node. Finally, the head node is returned. As an example, the process of creating a circular linked list with elements 10, 20, and 30 is demonstrated step by step. Here is the code for inserting a node at the beginning of a circular linked list. A new node is created. If the list is empty, the new node will point to itself. If the list is not empty, then the new node is connected to the head, and the last node is updated to point to the new node. Finally, the head is moved to the new node. An example of how a node with the value 5 is inserted at the beginning of a circular linked list. The last node is updated to point to the new head, maintaining the circular structure. Here's how to delete a node in a circular linked list. If the list is empty, there is nothing to delete. If the head node is the one to be deleted, then if it is the only node, the head is set to none. Otherwise, the last node's next pointer is updated to point to the second node, and the head is moved to the second node. An example of the steps involved in deleting the head node with the value 10. Here is the code for traversing a circular linked list. If the list is empty, there is nothing to traverse. The current node is set to the head. Each node is processed, and its data is added to the result. The current node is updated to the next node. The loop continues until the current node returns to the head. An example of the traversal process in a circular linked list containing the values 10, 20, 30, 40, 50, and 60. The result will be an array of values. Here's how to search for a specific value in a circular linked list. If the list is empty, it returns false, indicating that the value cannot be found. The current node is set to the head. Each node is checked to determine whether it is the needed value. The current node is updated to the next node. If the value is not found after traversing the entire list, the method returns false. Here's a circular linked list with nodes containing values, and the search path for the value 30 is animated. Let's analyze the time complexity of operations in a circular linked list. We will compare it with a singly linked list. Insertion at the beginning has a constant time complexity in both singly and circular linked lists. Insertion at the end takes linear time in a singly linked list but constant time in a circular linked list, provided a pointer to the last node is maintained. Deletion at the beginning is constant time for both. Deletion at the end is linear time for singly linked lists but constant time for circular linked lists with the last node pointer. Searching and traversal both take linear time in both types of lists. The key advantage of circular linked lists is the constant time insertion and deletion at both ends when a pointer to the last node is maintained. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.